Hello everyone, welcome back. In this section we are going to move on to discuss the field effect transistors. And in this discussion we were particularly interested in the metal oxide semiconductor field effect transistor, and we call it MOSFET. MOSFET has similar usage as BJTs. They can be used as signal amplifier and electronic switch, as we discussed in BJTs. MOSFETs can be manufactured using a relatively simple process and can be made very small compared to BJTs. Now, there are two major types of MOSFETs. So one is called enhancement type. Another one is called depletion type. For enhancement type, which means normally the transistor is open, that means the transistor will not conduct any current under normal condition or without biasing. And for the depletion type, the transistor will behave like a closed switch. Probably you will have a better understanding after we have a further discussion on how the FET works. Now, this figure shows us the typical structure of a MOSFET. And the MOSFET basically has four terminals. And we have a body here, and on top of that, and we have two terminals. One is called the source terminal, another one is the drain terminal, or we call it source region or drain region. And between these two regions, and we have something covered by an insulating layer. Typically, is some kind of oxide in a silicon-based MOSFET, that is the silicon oxide. And on top of the silicon oxide, and we have a metal layer, and this layer will connect to, we call it a gate. Now we have four terminals, right? The body, the source, and the drain, and also the gate. Sometimes our body and the source will be connected together, and the transistor node will become a three-terminal device. In the application of most electronic switches, and these two usually will be tied together. But in some other application, especially in the analog application, and these two terminals might be separated. Now, if we don't have any bias voltage applied to the gate terminal, because the body is one type, the source and the drain will be another type. In this particular case, we have a body as a P type and the source and the drain as N type. And then we are going to form the two pin junctions from the body to the source and from the body to the drain. These two pin junctions will be back to back. And this junction will prevent any current flow from the drain to source. So in order to obtain current flow, so MOSFET needed to be biased. And similarly to what is required for BJT, if we can apply a gate voltage from here and with respect to the source, however, even though we have our gate voltage here, we will not have any gate current, because we have this kind of insulating layer here will block any current. In this way, the working principle of MOSFET will be completely different from BJTs. Two things will happen if we apply a gate voltage. If we apply a positive voltage here on the gate, And we are going to form a electro field. And this electro field, this will push away those positive charges, right? Because the gate is positive, it will push away the positive charge from the region underneath the gate. In that way, it will uncover some bound negative electron charge. And those bound negative electrons cannot move because they are fixed. And the electrons from this heavily doped and the source and the drain region will be able to attract to underneath this gate region. And then it will form a channel, right? This channel becomes N-type because now it's like electron-rich, right? Electron-rich material, we call it N-type. Now this form an N-type channel, and thus we call this kind of transistor is called N-channel MOSFET, or we call it NMOS transistor. Now we formed this N-channel. If we apply a voltage between the drain and the source, and the current will flow through this N-channel because we have an electron here, right? The electron can become a conductive charge. Now that's why what the term source to drain come from. And this is like a pipe, right? We have this kind of a drain. We will pipe the electron from the source to the drain. So the gate voltage, VGS, is required to accumulate sufficient number of mobile electrons in the channel. Right? This kind of voltage, we call it the threshold voltage. This value is related to the oxide capacitance. The oxide capacitance can be calculated by the formula here, and here the epsilon OX is the permittivity and the TOX is the oxide thickness. So the oxide capacitance can be calculated by this permittivity divided by the thickness. For an N-channel MOSFET, this threshold voltage is about 1 to 3 volts. When the channel is reduced, which means our VGS is sufficiently large, is larger than VT, and when the VDS is small, which means when the source and the drain voltage is small, so the transistor will most likely behave like a resistor. This resistance, it can be controlled by the VGS. Actually, the conductance of this channel will be proportional to something we call excess gate voltage. Right? This is effective voltage or overdrive voltage. Can be calculated by this VOV equals VGS minus VT, right? And then gate voltage, which is bigger than our threshold voltage. And this difference will give us the excess gate voltage. This excess gate voltage must be greater than 0 for the current from drain to source, because only this voltage greater than 0 and we can form the channel. From this figure we can see that, and when the VGS becomes bigger, and then the slope actually will change, and that slope representing the inverse of the resistance, right? The slope is the conductance. If we continue increase drain to source voltage, that is the VDS, if this VDS increases beyond a certain value, and then we're going to form additional electric field at the drain, from the drain to the body or to the source. And this electric field will become larger enough, it can will change the channel shape. And this change will make you generate more negative charge close to the source side, but the channel width at the drain side will become smaller. The reason for this is because if we have a larger drain voltage here, now at the pin junction at the drain side is reversely biased. If we have a increased drain voltage, and then we are going to form a wider pin junction, right? So the depletion region becomes wider, which also means we are going to form a lot of negative bound negative charges. This bound negative charge will push away this free mobile electron charge, which will narrow the channel here. Because of this tapered shape of channel, so the resistance of the channel will increase. So in that way, so the IV characteristics of this curve now will no longer be a straight line as we see before, right? It becomes curved because the resistance now is increasing because of the narrowing of the channel. When we further increase our VDS, when the VDS is large enough, the channel at the drain end actually reduced to zero. The size of the channel reduced to zero. And this is called a pinch off. Right? Initially, we close the channel at the very end to the drain side. And this happened when our VDS larger than this VGS minus VT. And this VDS actually is the VOV, right, as we discussed before. And when the VDS larger than VOV, and we call the VOV overdrive voltage. And when VDS larger than this overdrive voltage, and then we close the channel. Now when the channel is closed, does this mean that our current, our source drain current equals zero? And actually, it is not. Even though the channel is being pinched off at the drain end, we still have a current flow. So if we look at the drain side, because the drain side we have a pin junction which is reverse biased in this depletion region, and we form a building potential, right? And this building potential, which have a positive charge close to the drain and a negative charge and close to the region underneath the gate. And even though here there's no channel, but any mobile electron or mobile negative charge when close to this depletion region will be able to be swept by this electrical field and to the drain. Just exactly happen what we see in the BJTs. Remember, in the NPN BJT, similar thing will happen, right? The electrical field of the reverse biased CBJ actually sweep the electron from the base to the collector region. And here, this depletion region here at the close to the drain actually is able to sweep the electron from here and to the drain side. And that's the way we still form the current or the drain current. However, when the channel is pinched off and the drain current now will become saturated, which means it does not change even we further increase our VDS, because the number of available electron is limited. So that's why we see this flat line here. Now this is the IV characteristics of the transistor. Even though we increase the drain to source voltage, and our current will maintain a constant value. Now this is the operation description for a N-channel MOSFET. And what happens for a p-channel MOSFET? For a p-channel MOSFET, we do need a n-type substrate. And then what we need is a negative gate voltage. So this negative gate voltage will repel the negative charge and left positive bound charge, and they attract those holes from source and drain to form a p-type channel. When we operate this device, we require this VGS needed to be less than 0, and also VDS needed to be less than 0, and VT here, or threshold voltage, needed to be less than 0 too. Right, here's the configuration for this p-channel MOSFET. As we can see, now the current still be 0. You cannot get any current out of this gate because of this insulating layer. But we do have this drain current from source to drain, and the drain here needed to be negatively biased. Now probably we have some better understanding of what is enhanced type and what is the depletion type. So the enhanced type means we needed to apply a voltage to the gate to induce the depletion and then induce the channel. And for the depletion type, so without any gate voltage, actually, so the channel is already formed. So that's the difference between the enhanced type and the depletion type. Actually, we can make P moles or N moles on same substrate. And here is how we can make it. If we have a P-type substrate, lightly doped, and we can create another region is here, and midly doped with N region. And then we can make an N-MOS transistor on the left side with source and drain being heavily N-doped, on the right hand side with source and drain heavily P-doped. And in the middle, we can separate them by oxide to isolate these two transistors. In this way, we can make an N-MOS transistor and a P-MOS transistor on the same substrate, and will be much easier to make an amplifier in this case, or some other applications like electronic switch or inverter. Now here I'm going to introduce the typical symbols we are using to represent these transistors. We have three symbols can be used. The first one will have an arrow from the body and to the gate, and the second one will have an arrow at the source side and pointing out. And these two actually are 4-terminal devices. So the third one is by connecting the body to the source and to generate a 3-terminal devices. And all of these actually are used quite often. Now this is the N-type enhancement MOSFET. For the P-type enhancement MOSFET, and we have an arrow pointing to the body, because now the body actually is N-type. Or we can put an arrow pointing into the source. So for the first two are also 4-terminal symbols. The last one is a 3-terminal symbols which will connect the body to the source. Okay, there's some basic introduction to the field effect transistors, and I mainly focus on metal oxide semiconductor field effect transistors. And the next session, I will discuss the IV characteristics for these transistors. See you next time.